Welcome to the Databricks Skill Builder series. We're glad you're here.
Okay, so I'm going to go ahead and get started. Carrie, my partner should be joining here momentarily, and she'll be handling questions. So I want to welcome everyone to today's customer skill building session. Let me start by asking Carrie or anyone else, perhaps through the chat, can you see my slide there that says model serving?
Yep, we can see it.
All right, excellent, excellent. So, my name is Art Rask. I'm a solution architect with the Databricks Field Engineering Organization, and I'm happy to have the chance today to talk to everyone here today about model serving, which is our name for a new capability in Databricks that is designed to enable real-time serving of trained machine learning models so that you can integrate them with an application or a solution in a variety of ways that are, it's basically highly flexible. It gives you just the ability to plug that model into almost any application or solution that you're building. And we're going to explain that in detail and talk about how it works and show you a demo of what how it is set up and turned on, and then also importantly address a little bit about how it's priced, how you can kind of predict your costs when you use it, and speak a little bit about the roadmap as well, and touch on observability and monitoring, which is also kind of from a production perspective an important set of issues for any platform capability that you're going to use, certainly including this one. So I want to maybe pause for just a second before we dive in, though, to let my colleagues introduce themselves. I'll pass the baton over, and if you guys want to do a quick intro.
So hi, I'm Carrie Ross. I'm also solutions architect here at Databricks, and I'm here to help field any questions. So just a little bit of logistics. If you have any questions, just put them in the chat or raise your hand, and I'll make sure that we can stop and address those as we go along. So thanks everyone for attending.
Okay, great. And I'm also joined by, hold on one sec, by Samaya, who is another colleague of ours. And let me just make sure she is promoted to panelist. Okay. And we should have Samaya popping in just momentarily. And Samaya, would you like to introduce yourself real quick?
Hi, can you all hear me?
Yes, we can.
Perfect. Hey, thank you for promoting me as a panel member. I'm Samaya. I'm a solutions architect here with Databricks. I focus primarily on the machine learning and the data science parts of the product here within Databricks. I'm based out of Austin, Texas, and I'm excited to be here. Feel free to post any questions that you might have in the Q&A session, and we'll get to it as soon as you post them. So thanks.
Absolutely. Thank you. So with that, we'll go ahead and dive in. I'll kind of kick off the slides, and just to make sure we're good with visibility, you guys can see the slide change to the Lakehouse slide. Is that right? Okay, excellent. So we'll start kind of at a high level, and very quickly we're going to move down into the nuts and bolts of this. But just to kind of position model serving, it's a capability that lives within the larger Databricks Lakehouse platform. And the idea of the Lakehouse is to have a simple and a multi-cloud open platform that enables organizations of all kinds to build advanced data and AI solutions in a way that is agile, that is cost-effective, and that is almost infinitely scalable. The way that we, kind of the philosophy of that architecture is grounded in the cloud data lake technologies that we have today with all the major cloud providers. Databricks uses data and consumes data out of the cloud object stores that the major cloud platforms offer, whether it's S3 in AWS, Google Cloud Store in Google Cloud Platform, or ADLS Gen 2 in Microsoft Azure, which has the positive kind of attribute that it's an extremely low cost, highly resilient storage layer that is also open, and is kind of the first building block towards an architecture that retains openness for customers, that avoids data lock-in or format lock-in or vendor lock-in. And on top of the data lake store, we have innovated with something called Delta Lake, and many of the founders of the open source Delta Lake format were from Databricks. Of course, it's also got many contributors from organizations all over the world. But Delta is an essential element that allows, it's a format, it's just a file format essentially, and a protocol for how to conduct updates and changes to that file format. It brings the benefits of data warehouses in terms of ACID transactions, concurrency, reliability, et cetera, to cloud data lakes. So it brings performance, reliability to the data lake, which allows us to, and that's where the term Lakehouse comes from. It's the foundational layer that gives us the best of the data lake and the best of the data warehouse. On top of that, Databricks includes a governance layer called Unity Catalog, which provides for cataloging and discovery of data assets, and importantly, governance of access and permissions to those assets. And that's true whether they are structured data assets or unstructured data assets, files, et cetera, that are in the data lake. And then finally, kind of what the real point of all this is that the top layer here is the capabilities in the Databricks runtime to support essentially the full scope of modern data and AI workloads and use cases with the Databricks runtime and the engine, which is at the core of it is open source Spark. But that enables us to support classic data warehousing types of workloads for relational data warehouse scenarios, data engineering for ETL and transfer and data pipelines, et cetera, that are almost always a part of any data and AI solution. An important thing that is that differentiates the Lakehouse from traditional, let's say, relational data warehouses is also the data streaming piece here, which allows that platform to deal with data that's in flight, if you will, near real-time data that's constantly changing, constantly being added to. This is an excellent platform for handling those kind of use cases, perhaps with integration to Kafka or Azure Event Hubs or other streaming data sources like that. And then finally, part of the bread and butter of the Lakehouse as well is data science and machine learning. In fact, it's a big part of sort of the provenance of Spark and Databricks both is supporting the requirements of advanced data science and machine learning and AI. And that's where we are. That's the reason it's kind of color-coded there. It's green. That's really the focus of today's talk, is this capability that lives within that data science and ML part of the Lakehouse. And specifically, the Lakehouse in general, and the Databricks product in general, rather, provides all the things you need for the full end-to-end MLOps lifecycle. That starts with featurization and data preparation, kind of touching on the data engineering part of that previous slide. But then also moving into the parts of the machine learning lifecycle proper that are unique to machine learning, like featurization, like model training, experimentation, kind of iterative experimentation with models, hyperparameter tuning. And the whole process here is infused with an open source framework called MLflow, which automatically is able to track changes to experiments as data scientists are working with them, and track the changes in performance or accuracy of those models, such that it's a lot easier than if you did not have MLflow to be able to kind of confirm the progression of your model towards the level of quality that you want, and be able to pick the best combination of parameters and libraries and training algorithms that are going to produce the the model that you actually want to put into production. And then finally, the MLflow has the concept of a model registry, which allows the data scientists or the ML engineers to sort of register and track the versions of the models or the versions of the experiment that are actually suitable for use in production, or at least in a staging testing environment, and then version those over time as well. So that kind of brings us up, tees it up to the point of having ML artifacts that are usable in production and that are reproducible in terms of having all the information about dependencies that's required to successfully use the model in production. And then finally, out here on the right side, rather, the end part of this diagram here is what we're here to talk about today, really, which is how do we make those models consumable in production in the way that's appropriate for the solution architecture that we want this ML capability to be part of. And that part of the Databricks platform includes model serving. It includes the ability to score with these models in large batch type of scenarios. And it includes the kind of the plumbing to enable monitoring of these models in production to track feature drift, concept drift, or other issues that may kind of arise as a model is used, so that the team can continue to make sure that it's meeting the needs of the business, or even improve its ability to meet the needs of the business. So that brings us, kind of in that larger scope of the ML platform with Databricks, brings us to the focus of today's talk, which is model serving, right? When we talk about model serving, what do we mean? Let's position that real quick in terms of the different ways that you might make a trained machine learning model available to use in a data pipeline or in a custom application or a website, as the case may be. We sort of conceptually think about a couple of key ways that you might utilize a trained model. The very common one is batch prediction or batch model use. And the idea there is once you've trained a model, or once your data scientists, machine learning engineers have trained a model, you may want to use that model as part of a data pipeline or some scheduled process or some scenario where you need to take large volumes of data and on a regular basis or somewhat ongoing basis, make predictions against the incoming data with the model, and then output, the predictions probably with the original data as well as a resulting data set. And then, process that downstream through your pipeline to whatever business process you're supporting. But the key differentiators there being that with batch, and I'll go ahead and jump to the next slide because it kind of calls it out. With batch, the latency that's required in the business process typically is on the order of minutes or even more. So maybe you need to score all the transactions from the business day to categorize them in some way, maybe do a classification on them or a segmentation, and you do that in batch in a sort of a large number of records, perhaps millions of records need to be scored and done, and maybe it's done every few hours or even every few minutes, but it's still a kind of an unattended batch process. That's a very common way, and that's easily supported with Databricks. Streaming, I mentioned, is another important part of the Lakehouse platform. So if you have data that's coming through on a continuous basis where you're doing near real-time processing, and you need to, as records come through, score them against a model so that you can maybe classify them or segment a customer transaction or predict fraud, for example. Those are scenarios where we might use streaming to push that data through a pipeline, more on the order of seconds to minutes, right? And the volume might be thousands of records per second, but it's not necessarily tens of millions or hundreds of millions of records that you might do with a batch process in a single run. The cost of that does go up a little bit. So in terms of the requirements of standing compute for doing streaming processing, it's not the cheapest option. But if it's what the operational requirements are, then that's what the platform enables. And then the sort of where we are with the focus today is the scenario here, the third option, with scoring against a model where you need to make that real time, if you will, or real time or on demand integrated with some solution or website or application where the interaction typically of a person, but it could be machinery or other things, requires the model to be called on demand, usually with a small set of records, maybe just one record, maybe a few, to produce some prediction that is then integrated into the behavior of the application, integrated into the user experience, or maybe even used to do sort of corrective action on some machinery that's running. And at a technical level, that's the idea, is to be able to expose the model itself as a REST API, which from a developer's perspective, a software developer's perspective, is sort of, as long as you can make it a REST API, you can tie it into just about anything, right? So your website can call a REST API, a tablet application can call a REST API, an embedded app in some machinery can call a REST API. And the idea of the model serving feature that we're here talk about today is Databricks making it possible to take your trained model and expose it online as a REST API that you can securely call from an application, and with low latency and potentially with high throughput in terms of queries per second and concurrency, be able to support calls from your application to provide the machine learning capabilities of the application. The trade-off there is it is a little more expensive from a compute perspective, and it's not necessarily the approach you would want to take if you have the choice for handling, let's say, millions or hundreds of millions of records. There we tend to stay more in the batch perspective. Just to kind of complete the picture, and it's not really the focus today, but there is the ability in terms of the full scope of scenarios that you might use a trained model. There is the ability to take one of these trained models and export it in a serialized format and push it out to an edge device, something that maybe is disconnected some or all of the time, becomes part of a piece of hardware or something, and is natively hosted in that hardware. That's really not what we're here to talk about today. But in terms of all the range of capabilities, that certainly is one of the options. So this being our focus here with the REST API, let's look at maybe one or two, in a visual sense, some sample architectures that might use this. I sort of verbally described some of this a minute ago, but the idea here is, if we look on the left side of the screen, this is pretty much where Databricks plays in the architecture. There would, of course, be the pipeline, the MLOps pipeline, where the data scientists train the model, prepare the features, do all the experimentation to produce the actual trained machine learning model. That's kind of what was on the previous slide. And for our purposes here, I've just sort of, collapsed that down into a simple little box. That all happens with the interaction of the data scientists and the ML engineers. And when they get to the point of having actual trained models, those are registered in the model registry. Again, the MLflow framework is the thing that enables all of that, and MLflow is embedded in Databricks, which gives you then a library, if you will, a registry actually, of trained models that you can reference. You can use them in batch scoring, some of the other examples that we mentioned on the previous slide. But as far as model serving goes, what this feature does is in a few clicks, you can take any one of those models and spin up what we call a serving endpoint, a model serving endpoint, which is basically live compute that exposes the ability to score against that model as a REST API endpoint. At that point, and you see that at the bottom here, kind of the bracket that says that's all within the scope of Databricks here, right? But at that point, that REST API endpoint can be called by just about anything. So one use case that we do, these are actual kind of things that we do really see our partners do. Let's say you're building a website. You have a website that presents content on the internet to all comers, and you need to put ads and offers embedded in that website content, maybe based on cookie information or other profile information about the user, or maybe the location where the request is coming from. Your website needs to be able to optimize what ads to place on the web pages, right? Or what offers to present to that particular user. That's commonly done with some sort of a prediction model or a segmentation model that you might build with Databricks, expose as an API endpoint. And then the code in your website, JavaScript code or whatever it is, could then call that REST API endpoint as the page gets rendered to decide what ads and offers to put into it. Another example might be predicting customer churn risk. So you might have a call center and there's an application that supports the call center. Your call center reps, when they take an incoming call from a customer, they might be able to resolve the customer in your CRM system. And as they're kind of handling that call, whether might be a support call or some other kind of thing, it's often useful to have some real-time idea of the churn risk of this customer. Is this a customer that we think we're at a risk of losing? And is that, would that be a negative impact on our business? Do we want to take some kind of action to try to reduce the churn risk? By being able to have that application call a REST API with the current customer information that your rep is on the phone with, you can get that churn risk and then build the application to suggest different courses of action to the call center rep based on the churn risk. And typically that might also be based on the value of the customer, perhaps using customer lifetime value techniques or something like that, where you could decide what made sense to try to retain that customer. And then finally, just another example to kind of talk about different use cases, different businesses. Another scenario where this would make sense is loan origination. So you might have an application that's used by folks that process mortgages, that originate mortgages in a bank or some other organization like that. And they need to, when they go, get the information about the applicant for the loan and information about the property that they're looking for a loan on, assuming it's a mortgage, but it could be any kind of loan. That app might want to, with that specific set of information, we're not talking about millions of things, we're talking about that specific set of information for that loan application. The app would then in real time call that REST API endpoint to get a risk score or to get a recommendation for the terms to set for that loan, the interest rate, the collateral requirements, the down payment requirements. Those kind of things might be set dynamically based on calling that REST API input. Now, of course, the possibilities go far beyond this. This is just an idea to kind of just present some of the use cases where this would fit into a larger architecture, and kind of land the point that these REST API endpoints can be plugged into just about any kind of application, ranging from a website to a traditional desktop application, a tablet app, whatever. So I'll go ahead and move forward here. Of course, to talk to you about how we're going to show this, we're starting with what is model serving, of course. We're already most of the way done with that, but then we're going to move into a demo. I'll show kind of how you set it up, how it looks in action. It's actually very easy, and the demo doesn't have to be very long. It's a pretty quick process. And then we'll come back and talk about pricing, how these things are priced, how you might predict the price given a certain workload, and then talk about monitoring, how the platform allows these things when they're being operated to be monitored, and how we support automated deployment in terms of a CI/CD timeline. And then time permitting, we'll also talk a little bit about roadmap. And then any point in here, we also welcome questions. You can ask questions while we're going through this, or save them to the end, whichever you prefer. So, given kind of the context of what model serving is for, what it's about, what we do in Databricks is the idea is to be able to support that capability and do it in a way that is essentially self-managing or largely self-managing, not requiring the customer or the engineering team to stand up independent compute resources, but really make it just a seamless push button part of the Databricks platform. And in doing so, to make it have that be production grade, right? So this is not something that's meant just for testing or for experimentation. It's meant to be something that can sustain high availability requirements, support low latency, like on the order of tens or hundreds of milliseconds latency, that is serverless in the sense that you don't have to provision VMs or do any of that kind of level of management, and that has the ability to scale as well, so that as the load from an application might go up or down during the day or during seasonal periods, the endpoint that you have pointed your application at can sort of transparently add capacity or take capacity away, or even during quiet times, just go to sleep altogether to optimize cost. Those are all things that are attributes of the model serving capability, and we'll show that and talk about that as we go through this. Another important thing about model serving is by having it in Databricks, our goal was, from an engineering perspective, to make it unified with the other aspects of the Lakehouse. So when you deploy a model with model serving, not only does it do that thing that we talked about, but it is able to easily integrate with the other supporting capabilities of the Lakehouse. That would include, let's say, feature store. So if that model requires feature lookups or feature resolution that uses the online feature store capabilities of Databricks, these models, when they're hosted in this way, can make use of that. And the monitoring and the governance of these models is embedded or integrated with the monitoring and governance of the Databricks platform as a whole. So it keeps things kind of cohesive and avoids the scenario where your solution is like a huge collection of Lego blocks all kind of glued together. It's more of a unified solution in a single platform. And then, simplicity. That's one of the themes of many things that we do at Databricks, the direction that we're taking with many of our capabilities. And as you'll hopefully see in the demo, this is a very simple process to deploy these things and to monitor them. So a couple of key things, and this just kind of reiterates some of the things I said, so I'll move through this slide quickly. But I did call out the production grade nature of this capability. This feature of Databricks model serving did go generally available in March, so like the first week of March. So it is a generally available feature at this time. And it's designed for low latency. So that could be, calls against these REST APIs that are as low as below 100 milliseconds. Throughput, if you provision the right level of capacity, our service is engineered to potentially go as high as 3,000 queries per second. The availability SLA is 99.5%, and scalability is baked in. So when you see how we provision these things, you'll see that the ability of the endpoint to scale the amount of compute behind it is just part of the service. It's baked right in. And that gives you the ability to optimize cost as well, because the cost is going to be elastic along with the compute capacity. And we do have, the work baked into this to be able to deploy these things in a secure manner. Private link is supported. We support IP allow lists to limit the input, the clients that can actually touch your API if that's the way you want it to be. So it's suitable for sort of enterprise grade security situations. I won't talk too much or kind of repeat the points that are in these other two slides. You can kind of see them and review them in the recording, of course, but I already mentioned how this is integrated with the other aspects of Databricks, and simplicity and manageability is kind of a key part of the design. And we'll touch on what that means as we go through the demo. So I'll go ahead and tee up, get ready to switch over to a demo. Samaya, do we have any questions in the question window, or? We do. I don't see any right now. So. Okay, good.
Just getting off of mute, but no questions.
Okay.
But although we do encourage, people to come up with questions if you have any. Absolutely.
Yeah, and of course, it's a webinar, so we can't have a conversation, but you can put your questions into the chat window, and we'll address them. So verbally and in the chat window as well. So let's go ahead and take a look at a demo of this. To launch the demo, and let me just confirm, Samaya, can you see my Databricks screen now, the browser?
Yes, I can. Yep.
Excellent. All right, cool. So where we are right now is sort of the landing page, if you will, of when you would first come into Databricks. Most commonly, you would just land here at the home page of the data science and engineering persona. And to get into model serving, because that is an ML-oriented capability, first thing I'm going to do is go up here in the upper left and switch the persona using the persona switcher to the machine learning persona in Databricks. And you'll see that the menu here on the left side changed to kind of make more prominent the features that a machine learning user would typically want to make or be able to access quickly, such as experiments, the feature store, the model registry, etc. And the model registry is where we're going to go in to deploy an endpoint. You'll see also, though, that there is the last option here is serving, and that is the entry point for model serving. That was added to the menu here as part of the model serving feature. And that's where you would go in and look at currently provisioned endpoints that you've set up. But I'm going to kind of start from the perspective of somebody who's just getting started. And to do that, I'm going to go into the models button here. That's going to give me, it's going to show me the model registry. So this is the MLflow model registry, all the models that have been registered in this particular workspace. And I'm going to filter that just by my models, the ones that are owned by me. And I've got a couple of things here. The one I'm interested in today is this customer segmentation model. So I'm going to click into this, and this is a model that's designed to kind of segment customers based on some simple information about their spending patterns, like the amount of spending activity that we know about this customer, what we think their income might be, and also what their age is or what their age range is. This is a model that's designed to be integrated, into our shopping website, perhaps, or to do ad placement, where we have a little bit of information about who we think the consumer is. We want to segment them. Do we think this is a big spender, a small spender, a medium spender, so that we can make decisions about offers and ads and promotions for this customer. You'll see that we're starting here, by the way, in the model registry, kind of consistent with that earlier picture. I'm not going to go through the whole model building lifecycle or the featurization. We're kind of picking things up here for the demo with the point where we already have a model. It's already been trained and we've decided it's appropriate and it's been registered. And we've got right now version 1 of this model in our registry, and it's been tagged as ready for production here, as you can see in the stage. So how do we make this available through model serving? How do we make this a REST API endpoint? It's actually quite simple. Up here on the right side, on the right corner up in the top is this use model for inference button. I'm going to click that. And you see we got a couple options here. The default, or the first option, is real time. And that's where we want to be. And we're able, as we set this up, to pick the model version that we want to expose. In this case, it's just the one, but there could be more there depending on how, where we are with this model. I'm going to give this model endpoint a name. So this is going to be the internal name of my endpoint that serves the model. And I'm going to pick a compute option here, or basically a amount of compute capacity to provision for the endpoint. And the options are very simple: small, medium, and large. And this goes back to the idea of simplicity that we talked about, and that this is a serverless approach to providing the endpoints. We don't get into a whole lot of knobs and switches and details of how these things get set up. You just pick small, medium, and large. And the key thing that differentiates these is the amount of concurrent requests that the endpoint is designed to be able to support. So if you think it's going to be a fairly lightly used service, that at most maybe 4 concurrent requests would come through, small is appropriate. And these different options allow you to go up to 64 concurrent requests. And you note that it says 0 to 4, 0 to 16, 0 to 64. That's because the endpoint, although it has that top end, 64, for example, it is actually able to dynamically scale to lower levels of concurrency if the traffic is low. And what that means is you save money. So you don't have to always pay for 64 concurrent requests. Maybe most of the time you only need enough compute for 10 concurrent requests, or let's say 12 concurrent requests. It could run at that level most of the time, but then automatically scale up to the higher levels when you have bursty periods where there's a lot of traffic. So for this purpose, I'm going to pick small. Another key thing, and this is the last thing we'll say about this before we click create, is the scale to 0 option. With those endpoints, you can set it to where during periods of inactivity, the endpoint will actually shut down altogether, and the cost of it will be 0 at that point in time. And then if a new request comes in, it will light back up and bring the endpoint back up. Bringing the endpoint back up usually takes on the order of 10 to 20 seconds. So don't assume that that's going to be immediate. But it's certainly not minutes or anything like that. It's around 10 to 20 seconds. If that's not a tolerable startup time, at the end of a period of inactivity, you can certainly just disable that by unchecking the box, and the endpoint will never scale all the way down to 0. It'll just scale down to a low capacity level, but it will always stay immediately responsive. So that's kind of a choice you can make to balance cost versus responsiveness of the endpoints. I'm going to go ahead and check it to be on here, and I'm going to click create endpoint. Now, the demo, as far as creating the API endpoint, is actually done now. That was the whole process. We just clicked use model for inference. We made a couple of choices, and the rest is going to be handled by the platform. So what we'd be able to see here is if we stayed and watched this, we could see the events in the log tell us that this thing is getting spun up. It's creating the containers for this. It's going to get the model from the model registry, bring it into the containers. It's going to use the information in the model registry, in the manifest for the model, to resolve all the dependencies that are required. So does this require, let's say, TensorFlow or sklearn or other dependent libraries to be able to score the model? If so, it'll get those as well, put all that in the container, and then bring it up as a callable REST API endpoint to make this available.
Hey, Art, we do have a
Sure.
question that's come
Okay.
in.
Yeah.
Question is, when serving a model, which cluster size do Databricks use by default? Let's say for small compute. So I know you've like covered details about, how to decide your cluster size and such, but is there a default that we point to?
Yeah. So there is no default. And I think there may be two ways to interpret that question. I think one is like, if you don't pick anything, is there a default in that dropdown? And there's not, you have to pick one. If the question is a little deeper, like what cluster size, certainly if that came from a Databricks user, they may be used to provisioning, say, Databricks runtime clusters where you pick VM sizes or pick other things like that. Or and part of the point here is that you don't have to do that. You just pick small, medium, or large, and we provision the compute underneath that's optimal for that task. Does that make sense, Samaya? Do you think that addressed the question, or?
I think so. So
Yeah. Okay.
if you do have a follow-up, please bring that back on the Q&A.
Yeah, just jump in. Whoever asked the question, just jump back in the Q&A if that was not clear, or if it didn't fully answer the question. So.
Perfect. Thanks, Art.
Okay. Yeah, cool, no problem. So so that endpoint, if we can go over here now to the serving section, and go to created by me, we just created CSP segmentation 1. I also had CSP segmentation 2 here ready just in case, right? It looks like we actually had enough, with the question coming in at a good time, it gave us enough time for this to be ready. Again, typically creating the endpoint from 0 when it doesn't exist, it initially takes usually maybe like 2, 3, 4 minutes. But then once it's there, even if it scales down to 0, it would only take like 10 to 20 seconds to come back up. But that initial provisioning, because it does the things that I described to you, usually takes 2, 3, maybe 4 minutes. Good news is this one's ready to go. So we can actually, I'll say a little bit about what's shown here, but first I'll just show you how we can very quickly do a sanity check that this thing is actually working and is turned on. We can paste in some payload that we know is the valid request content for this particular model, and just click send request. And you see that the model it just called the model and returned a prediction. So for these particular parameters, our segmentation model would think that that's a small spender. But if we change some of these things, we might get a different result. We change the spending score. We may get medium for that particular set of parameters. So the details of the model don't really matter that much. This is just for the sake of example. But you can see that it is calling the model. It is returning, the appropriate result from that model based on the parameters. And of course, you can see it's nice and snappy and quick. That's essentially the end of the process in terms of provisioning the endpoint. There are also little bits of boilerplate in here so that you can test this from a curl command if you wanted to actually get outside of Databricks and test this from a command window, or some Python code that you could use to call it. In each case, you would need to provide, a little bit of basically like a file containing the same data that I put here that has the things that you want to issue as parameters to query the endpoint. And like I said, I mean, it's simplicity is a design principle here, and that's pretty much the process of making the API endpoint available. Here, as you can see on the screen, there's some potentially useful information. I'm gonna actually switch over to the other one that I had created here, just because we might actually be lucky enough to see some information in the logs here. There's baked into the UI, there is some ability to monitor in terms of latency, request rate per second over time, error rates. So if you're getting any kind of errors thrown by your model, that's obviously a good thing to know. CPU utilization, et cetera, memory usage, and how much this is important if you want to kind of see how cost might be changing over time, is the provisioned concurrency. As this were set to be able to scale to a larger amount, you would be able to see that over time. So there is some pretty decent monitoring here, just visually right in the console. You can also look at the event history. And you can see service logs, and this gets pretty deep down logs about the service or the build out of the model in terms of the dependencies that are in the endpoint. And these, of course, can be saved off and you can parse them or do whatever you want with them. Now, of course, in a production scenario, you might not want to do all the stuff that we just did interactively. You might not want to use the user interface. You might not want to see all the graphs are nice. You might not want to see them. You might want to have that data extracted and put into a enterprise monitoring tool that you use for your company, and perhaps even set up alerts that would let you know if, let's say, the error rate starts to spike or something like that. And for that, we'll kind of switch back to the slides and talk about how that kind of observability and deployment scenarios are supported. But before we do that, I want to go to pricing. Obviously, what does it cost is an important part of this discussion. So we'll switch back to the slides and pick it up there. And again, any questions you have, feel free to drop them in the Q&A window. So starting with pricing, the pricing is related to the size of the compute that you choose here, and the scaling, the auto scaling of that compute capacity over time. That's kind of how we the price is just a function of that, basically. This just summarizes the things that I talked about when we were setting it up, kind of how the different sizes of compute work. The way the price is set is the key driver is concurrency. So how much concurrency, sorry, is provisioned right now determines the running price of the service. So remember, that's this range here in the drop downs. Let's say I picked the medium. At any given time, that means my provision concurrency is going to be somewhere between 0 and 16. And that number times the price per DBU is going to be the price, for that period of time. Well, what does the DBU cost? The way you can find that out is just click over here to go to the Databricks website, go to pricing for model serving, and then you can see what the price is, right? So it's now it depends a little bit on which region in your cloud provider this you're using. But for example, here in the US East region of AWS, it is 7 cents per DBU. So, and we'll go through a calculation here in just a minute that plugs that in to get an actual price. But you'll see, just for the sake of awareness, that price may change as you look at different regions. Right here, it's 8.4% in Frankfurt. And as we look at different clouds, there might be different prices depending on the different regions in the different clouds. There's not a huge difference. As you can see, we're talking maybe a difference of a penny or two per DBU based on those regions. But that's where you can get that information as far as what the price is. And then you take that and you plug it into the level of concurrency that you currently have provisioned. So let's look at an example. Let's say we have a model, we set it up. It was set up to be able to scale to 0. And let's say that it was, for this example, it would have had to be a large endpoint because we're going to go as high as like 28 or so concurrent requests. So that would have had to be able to scale from 0 to 64. So this would be a large endpoint, but it would be set to scale to 0. And at the beginning of this time period, let's say we have no traffic. That means the model or the endpoint would have scaled to 0, which means shut down the compute, and it's not costing anything right now. It's the cost is 0. But then let's say, things start happening, the workday begins, or whatever it is that drives activity in your solution. Some requests start to come in, people start logging in, and suddenly we're supporting 20 concurrent requests. That might be, so let's say just within any 1 second window or so, give or take, we're having to support 20 concurrent requests. That will cause the endpoint to scale up to 20. And the price for the period after, from starting then for however long that continues, is going to be $1.40 per hour. How did I get that? I took the 7 cents per hour. So we're assuming this is maybe US East and AWS. 7 cents per hour times 20 is $1.40 per hour. That's the price. Now, when we scale to 0, we also have to account for a small detail. When the way the service works, when it starts up from 0, when it initiates the endpoint, when it was scaled to 0, it will it will kind of charge a 2 cents per, a 2 dBU. It will charge a 2 dBU launch charge for that endpoint. So if it had gone to sleep and traffic started up, just to bring it up is a 2 dBU launch charge. In this case, it's 14 cents because 7 cents is the dBU price. And the idea that the point of that is that behind the scenes, we have to manage the capacity and keep a certain amount of capacity available. And so this just helps defray the cost of the underlying capacity. It also gives you as the user of the service sort of a way to think about when does it make sense for us to scale to zero? Like if you think your periods of inactivity are going to be like, a couple times per hour, you're going to get quiet and then start back up and then get quiet. Because of this, this charge makes it to where it really only makes sense typically to scale to zero if your quiet period is going to exceed, let's say, 1 to 2 hours, right? And you can kind of do your own math for what makes sense to you. But if you work that out, you would see that it only makes sense to really scale to zero if your quiet period is going to be somewhat extended, more than just like 5 or 10 minutes. So hope that makes sense. It's really a small part of the overall cost, but that's part of how the price gets calculated. So we, the endpoint spun up, it's supporting 20 concurrent requests. And then let's say that the traffic increases a little bit, even more people come online using your solution, whatever it is, and the traffic increases to 26 concurrent requests. So this is where we get to kind of introduce another little detail about the way that the scaling works. You remember there was these ranges here for how many concurrent requests any endpoint can support. As the service scales, just the way it works, it's designed to scale in units of 4. So it will only add or subtract 4 concurrency slots each time it does a scaling operation. So let's say it was at 4 and the traffic increased. The next level it can go is 8. It's not going to go to 5 or 6. It's going to go up to 8 or some other multiple of 4 from the current level that it was at. So in this example, we had the traffic go from 20 to 26. In order to support 26, it's got to go to the next highest multiple of 4 above 26, which is 28. So that's the level that you would see it scale to. And doing our little bit of math, about 7 cents per hour times 28, the new charge rate for that period of time is $1.96 per hour. And then let's say finally that traffic goes down to about 8 concurrent requests. Everybody went to lunch or whatever the driver is of utilization. And you now only need 8 concurrent requests. It's going to drop to that level and your standing cost will be 56 cents per hour. So that's an example. Hopefully that explains kind of the life cycle of how this thing would scale up and scale down and what the actual price for running the model serving endpoint would be. From that, another thing that's just kind of worth mentioning is that concurrency is not necessarily the same thing as queries per second. So concurrency is like literally at any instant in time, the number of concurrent instances of a model that could be generating a prediction. But depending on how quickly your model generates predictions, it could be more or less in terms of the queries per second. So for example, let's say you've got a model that has a concurrency of 8, and the model takes 1 second exactly to produce a result, then your concurrency is going to be 8. But if your model only takes 100 milliseconds to produce a result, then you could, if you had 20 concurrency, you can actually handle 200 requests per second. Hope that makes sense here. This is just saying that, if I need to support if I need to support 200 queries per second, and my model takes 1/10 of a second to return an answer, 20 is the concurrency level that I would actually need to support that. So just some basic math there about how queries per second relates to the concurrency slots. Okay, so we're in the last 10 minutes or so here of the talk, and we're going to move into, as I said, into observability and deployment topics. So I showed earlier how the user interface itself presents some graphs of request rates and error rates and latency in terms of model execution time. But very often in an enterprise environment, you'll have a need as part of a larger monitoring strategy, perhaps, to extract that data in a flat file format that you can then, load into Datadog, let's say, or New Relic, or some other kind of monitoring tool that you're using at an enterprise level. And this solution is designed to support that kind of a situation. There is a part of the APIs, so the ability to manipulate serving endpoints, create them, modify them, delete them, is all exposed as REST APIs, just the Databricks APIs. And one of those Databricks APIs is a call you can make to extract a log of all the metrics for that endpoint. And so if you need to integrate this into a enterprise monitoring solution, you would just set up, a regular call to that endpoint to pull the latest logs, import them into your monitoring solution of choice. That's also how you would typically set up if you needed to have alerting. Model serving itself doesn't inherently support alerting. Like, let's say if the error rate goes above 1 per second or goes above 0, you might want to get an alert so somebody can go see what's wrong with the model. Or if the response time gets really, really slow, you can do that by exporting it into your tool of choice and setting up the alerts there. Or if you're not using any other tools, you certainly could actually just do that with Databricks. You can export these logs and import them into a Delta table with Databricks SQL and have set up a Databricks SQL alert that would generate an alert for you when certain metrics get out of a threshold that you want to set. So it is possible to do it just with Databricks, but often we'll see customers, integrating some enterprise monitoring environment that supports many use cases. From a deployment perspective, as I mentioned, it's great to see the user interface demo, and that's sometimes how you'll do it for dev or for testing. But for production, you typically want to make that part of an automated deployment. There is a full API in Databricks, just like we have a jobs API and a workflows API. There is now an endpoint API, which is basically a set of function calls you can use to provision, to modify, to clean up endpoints, and also to get those logs, as I mentioned earlier. So this is suitable for automated deployment processes. We also have a Terraform provider on the roadmap, not there today, but Terraform support for this will be coming. That's kind of, I'm moving a little bit quickly because we're down to the last 5 minutes. Wanted to leave some time for other questions if they come up, or also I can point out a few things about the roadmap for where this feature is going.
No questions at this point, Art.
Okay. All right. Sounds good. Sounds good. No worries. So we got 5 more minutes. So put questions in the Q&A if you like. I'll say a few things about roadmap though. Jumping ahead, this is actually things that we already talked about. But wanted to talk about things that are coming. So the capability is GA, as we said. We're continuing to work on it though to enhance it, and we'll be adding more features to it over time. One thing that can be useful in some cases is logging of the request response payload. This can play into doing diagnostics or troubleshooting, or importantly into maybe doing overall, monitoring over time of your model. You might want to log every request and response and then go back and do comparisons against ground truth, for example, or other things to measure the effectiveness of the model itself for whatever the business purpose is. And this payload logging feature will allow that to be a very simple thing to do. You just turn it on and it'll capture every request response pair, and you can do whatever analytics you want on that. GPU accelerated inference is coming. So you saw there was the small, medium, large compute options. Implied by that was that those are CPU driven instances behind the scenes. Some models require GPUs to do the inference, and a GPU enabled endpoint is on the roadmap as well. So that will be coming. That may touch on the question that somebody asked earlier. It wasn't said, but maybe they're wondering if there's GPU instances behind the scenes, and that is on the roadmap. Another one that's coming, we mentioned that this is suitable for for sub 100 millisecond latencies for models. We're doing continued work on that though to get even more aggressive and be able to support models with less than 40 milliseconds. So even better latency is on the roadmap. And this third bullet here actually touches on something that I kind of passed over in the discussion earlier. So maybe I'll explain what this is about, because that'll make what the feature is actually make more sense. So one thing that is often necessary in kind of the actual production lifecycle of a machine learning model that's part of a larger solution is some kind of A/B testing, right? So you may have a current version of this model in production, and then your data scientist may try to make a better model, and you want to deploy that, but maybe you don't want to break things if that model turns out to not be just as good as you thought it was. So you want to set up some kind of maybe an A/B test scenario, or the ability to route, let's say, just put it up into production and route only 10% of your current traffic to that model, and look at how it goes, make sure that it's stable, make sure that it's producing good results, and only then make it the full production model, or maybe even pull it back to do more work on it. So that's very easy to do. I have another example here of a deployed endpoint. And in this case, I've actually got two models, version 1 and version 2 of the same model, that are set up as independent endpoints. And I've got 85% of the traffic going to version 1, and I've got 15% of the traffic going to version 2. And the process for adding those is real simple. Like if I was going to add one to this, I would just go to add served model. I could pick my model and pick the version of the model, and then just set what the hope I can find my model. Yeah. Pick what version. I don't have a third version here, but you can see what the process is. And then I would pick what percentage I want to route to that version of the model. And that just gets added to my endpoint. And then I can kind of observe accordingly to see if it's something I want to keep. So I'm going to cancel that. So that's that's a inherent feature of the service. And one thing that doesn't do today though is that's pure round robin. The percentage is just round robin. But I might want to make it so that if a certain application client connects and it gets routed on the first call to the B version of the model, maybe to actually adequately go through the whole process, you want every subsequent call to go back to the B version. That's sticky traffic routing, and that's on the roadmap as well. So just FYI, that's coming. So that pretty much covers the roadmap stuff. And we're right about time, 59 minutes in. So we're looking good. I don't see any more questions. Samaya, am I missing anything question-wise? Or?
No questions.
All right. Okay. Well, I think that brings us to a close. And we're happy to have had the folks that we saw in the webinar today. And if you watched us on the recording, hopefully this addressed any questions that you might have. Thanks a lot.